welcome all of you here to our first show and tell for TinyML4D group of universities. No, and first of all, Marcos Senaro, that's our chair. No, he is the responsible for our group. He had a medical appointment, so he asked us to Brian, to Jeremy, and I to help you guys here. But the idea is the show is yours. It's for the network, for you guys to present, for your guys to show what you are doing with your projects, what we have learned so far, what you want to do in the future. So that's the idea, to be all of us together today. Okay. For our first show and tell, we have four presentations. Okay. We would probably change a little bit the order here for the people that are here. So probably we will start with University, Federal University of Itajubá, UNIFEI. It's my university, Brazil, and Renato and Mateus will present what they have done so far, what they learned with TinyML and what their ideas. We have another presentations from University of Malaysia, and we'll know about anomaly detection and in the temperature of AC motor. That's very interesting. Also, we have another presentation from University Javariana in Colombia. We'll talk about prediction of the material concentration in the contamination. So it's very, very interesting. And also from Samson, from University of Rwanda, he will talk about respiratory diseases for us. Okay. And well, I don't know, Jeremy, if you like to a few words about your experience about the show and tell, that you're a guy that know more than us here about that.
Well, just to start off, I'm a high school teacher in BC, Canada, and I've worked with a group for about 3 years now with TinyML, mainly working with edgeimpulse.com, doing motion, sound, vision, and the new FOMO. So with this presentation, the first one's pre-recorded, and we're still waiting for a couple of other people to check in. As Marcello says, we're going to make this hopefully reasonably casual, and we'll do a presentation. And if there's time, we'll have a little bit of question and answers. If we're pushing the time, we'll move on to the next presentation. And then at the end, we'll have some more question and answer period. Hopefully people sign up for the next month's presentation, November 24th. So for now, I think we're still missing Samson and Albelardo. Oh, it looks like Samson just joined. Samson, can you mic on just so that we can make a connection there?
Yes.
Hey, Samson.
Hello, good morning.
Morning. It's afternoon here.
Yeah.
Yes. Okay.
Are you ready to go ahead, Samson?
Yes, I can.
Okay, perfect. Before we start, I'd only like to see if Professor Vijay and Brian would like to say something to the group here, and before we start.
One thing I want to say is I'm super excited to hear what everyone's been working on. I always think it's so fun to see how people use TinyML in so many different ways that we haven't thought of. So super excited to see stuff. So thank you for making the time and joining us.
Super.
Yeah, I think Vijay said everything I was going to say.
Super. Samson, good morning and welcome, and the floor is yours. You can talk about what you're doing.
Let me just share. Okay, so basically, for us, we've been having a number of use cases for TinyML. I took a presentation now. This one says use case 3, but ignore that because we used it we were showing other different use cases in a different forum. So I just picked up that very fast. And so we are focusing on a portable rapid diagnostic kit for respiratory diseases. And just this was motivated by the fact that many people die because of respiratory diseases, according to statistics from the World Health Organization. And when it comes to diagnosis in Africa, there are a number of processes and labs that you have to attend to be able to get that. And also, we noticed that there's a lot of data on this is not so much. So we thought if we have a solution that can help in collecting data, that could lead to better solutions and also help solve the problem. So for our solution, is just an IoT self-diagnostic kit that is running on TinyML. So what happens is that we are getting exhaled breath and then monitoring volatile organic compounds from exhaled breath. And then we use TinyML to be able to predict if somebody is suffering from a given respiratory disease or not. So studies have shown that the volatile organic compounds from exhaled breath vary depending on if you're suffering from a certain disease or not. And the reason for using TinyML is because of the many advantages that we have. Connectivity is a challenge in Africa, so there's that. Then when it comes to healthcare, the issues of privacy, nobody wants to send the data to the cloud to be able to do that. Cost, and also to ensure that there's real-time inferencing, so you don't have to wait. So for our solution, basically, we were using some open data sets to test, but I think we have moved from that, and now we are using some gas sensors, volatile organic compound gas sensors that we've used to be able to collect data. And so once we collect the data, that looks at different components, that is alcohol, organic solvent, ammonia, carbon monoxide, and air quality from that. Then the data set that we initially used, there were 10 healthy people, and we tested on COPD. That is to be able to see if somebody is suffering or not, and some from air. And we were able to generate a TinyML model that was able to predict if somebody had COPD or not. So because of the success in this, we have now moved a step further, and we are now looking at collecting data that can be used for other diseases so that we can make this a reality to be able to cover a range of diseases. And so we are also using K-means anomaly detection so that you're able to tell if you have the right data that you need to do that. And the inference that we get is basically whether somebody is healthy or not. So from the initial study that was focusing on COPD, we were able to get, basically we used edge impulse to be able to train, and we were able to get different results. That is 95% for the flattened model. Then for the raw data model, we got 96. And we also used PCA to be able to train away from now edge impulse. We are trying to compare how the models were performing. And we are happy that we got a real benefit of using TinyML in terms of the inference time, the peak RAM, and even ROM usage. And we were able to compare and see that we were able to get that. And we also analyzed sensors. If we, for example, somebody does not have all the sensors that we're using, because we're using each sensors, and try to see the role or how it changes in terms of the requirements. And we managed to find out that with at least 4 of the sensors that we were using, somebody could still use that. But you know, the moment you reduce the parameters that you're checking, it also affects the accuracy that you're working on. And so that basically is the main thing that we have been doing. And now we are moving a step further. And we are happy that we presented a proposal at Data Science Africa, and we've gotten some money to be able to move further and be able to do more tests on other diseases. So we are happy that TinyML is really helping us and is growing in Africa. Thank you.
Oh, great.
Can we ask questions now, or should we ask questions later?
No, yeah, no, you can ask Vijay. Yeah, I think we have time.
Awesome, thank you. Very exciting, Samson. Curious, so what kind of devices would you ideally want to use? Like, if it's say TinyML.
Yeah, basically we are using the Arduino Nano BLE Sense to be able to. Okay. Yeah, that's the board that we are using. So we are connecting to the gas sensor that we are using to collect the data.
Okay. And is there a cost that normally, if it was this cheap, it would be good for a use case like this? How cheap would it is normally? Obviously more cheap is better, but what is like a dollar price we can say is cheap enough?
Yeah, in fact, that is what we are still trying to see, how we can be able to reduce to ensure that we make it as cheap as possible. So we can't still exactly say what would be the best, but we are working towards that.
Okay.
Yeah.
Well, thank you.
Quick question, Samson.
No, it's only to complement Vijay, and it's a good point because, of course, I think for prototype the Sense BLE it's good, but of course if you're not using, like, say, microphone or emo or all those several sensors that the Sense Arduino Sense has, there is a lot of other cheaper, very good processors that only the processor connect with the gas sensors that can lower the overall price of the project. So I think it's important.
Really impressive
Yes,
project. Really impressive, Samson. If you were to grab another gas sensor, do you have something in mind that you'd like to monitor, or the ones you're monitoring at the moment is just perfect?
Yeah, the ones we are monitoring, as you go to different diseases, there are different aspects that are monitored. So it will depend with the disease that we are focusing on at that time when collecting the data.
Great.
Yes. Yeah.
One thing interesting that I saw is that, for example, the amount of a RAM that we are use it is not change a lot with the
yeah, that was
the amount of sensors. Yeah, but I'm also curious about all the pre-process that we did with the sensors. You only take the raw data from the sensor and enter in your model, or you prepare something. You did some pre-preparation.
Initially, we got the data that we used had been pre-processed. So we are also trying to see now in the next phase how we can be able to do that, because it's important to pre-process before.
Yeah. Maybe it's interesting to see, for example, we have several this kind of multiple sensors. Maybe to have a window to go to the several sensors and got the information from pieces or for junks, maybe can help.
Yes, indeed. Thank you.
Yeah. Interesting. Yeah.
Marcello, we should be moving on.
Okay.
Are you going to run the video?
Yes. Let me take the video from the second presentation. After that, the students can talk about.
Hello. Good morning, everyone. I'm Mateus Delangélica.
I'm Renato Masteguim.
And it's an honor to represent our project and participate in the first TinyML show and tell event. We are very grateful for the invitation. We'll present to you now a little bit about how TinyML is helping us to develop our project. So, first of all, let us present ourselves. Ex Machina is a student's project from the Federal University of Itajubá, founded in 2014. And our main goal is to bring assistive technology to the university in Brazil, parallel with social work and 3D printing. At the present moment, we're focused on developing a low-cost 3D printed bionic prosthetic hand prototype. And here's some of our activities in the past years. So how we started with bionic hands, right? We started our journey in 2018 by a simplified hand prosthesis, which has been updated over time. And in these prototypes, it was only possible to identify if was received bioelectric impulse destined to the hand or not, like 0-1 logic, right? In a way that it was necessary to configure modules using a cell phone app so the processes could perform simple gestures. At the time, our project dreamed of being able to identify the patterns in the myoelectric signals of each one of the fingers, but we were still figuring out how that would be possible, right? We didn't have even an idea how we could get to this point. And then during the pandemic of COVID-19 in 2021, we had our first contact with TinyML at the S01 course with teachers Marcelo Rovai and José Alberto Ferreira. And we can say for sure that this course opened our minds for new ideas, giving us extremely powerful tools for our activities. And for the final project of S01, some members of Xmachina enrolled in the course worked together in a group to try to identify some patterns on bioelectrical signals. And our first ambitious idea was to differentiate the movement of each one of the finger of the hand with the data we've collected during the isolation period. The result of this job revealed us the way to achieve that goal that seemed so far to become reality in the past years. And we started our test using one EMG channel and 6 labels. And at the end of the course, we worked with 2 EMG channels with 4 labels, achieving 76% accuracy on 3-finger differentiation using test data. And after the end of the course, we continued working, now with 3-channel EMG, collecting data with Edge Impulse data folder that speeded up our activities. And during this test, we've noticed that gesture recognition was much more interesting for a real application. And this change made our first model with significant results, controlling our processes, making the gestures of OK, thumbs up, and rock and roll. And here's a short video from our first results. So along our activities, we've noticed that TinyML could improve a lot Xmachina. So we've decided to condense the S01 course to qualify our new members to use TinyML with Edge Impulse at the moment they entered our team. And at the end of the training period, the new members tested their knowledge by building a keyword spotting module on their own. And this module got us great results. Renato will describe further details of it.
So, our keyword spotting module was built initially with MFCC block with keywords classification, but wasn't successful because we had a small amount of data. So we noticed that Edge Impulse added the transfer learning block, and we decided to try it. And for our surprise, it works really well with our small amount of data. Then we decided to expand our dataset with the new members of the project. This module has 6 labels, which 5 of them was for gestures, and 1 of them was for noise or silence. And it works really well, especially in silence rooms. Our main problem with this module was the timing to talk. We had to talk exactly when the purple LED was turning off. So we are trying to improve that at the moment. So the Edge Impulse project of the month. We got a 3rd place with our keyword spotting module, and it was amazing to participate. Additionally, the sharing of the project by Edge Impulse and Arduino in their social media contributed to the other people to get to know who are we, who are Xmachina. So, and this also motivated us to continue with the idea of the alternative module. And it can be a difference in our project. So we will continue this project. So now let's see the winner video of this project. Dois.
Ok. Joia.
Rock.
Ok.
Ok.
So here we have some print screens about the social media of Arduino, Edge Impulse, and some of our teachers to show to you the repercussion about our project. And it's amazing to see how far we have achieved with this module. And for our project, Ex Machina was amazing participating in this competition. And currently, we are searching for sensors that can be used with our EMG or can replace it, trying to improve the signal capture. We are also searching for features and ways to reduce the noise of the signal and to improve our data and our data set as well. Our future work looks to improve the classification models we already have, like the gestures classification and keyword spotting, expanding the number of the gestures to facilitate the use of our bionic prostheses. We are going to implement one command to activate the keyword spotting module to improve the use of our prosthesis in a real situation with all other modules together. So this is our job using TinyML, which has dramatically improved our project. All of us from the Ex Machina, thanks for the opportunity and your attention. And especially thanks from Marcelo Rovai and José Alberto Ferreira for all the knowledge transmitted and the support for our ideas to become reality. Thank you very much.
Thank you, guys. Amazing job, amazing job. I'm very proud because I think this kind of work, they start to work without any knowledge about TinyML. And the last year, they did our TinyML course at University and opened their minds, like blew their mind, as Professor Vijay likes to say. It's amazing. And they saw a lot of possibilities to make new projects. But let me, guys, make question for them. Renato and Mateus are representing their group here. I think that you have time for a couple of questions.
Yeah, so it's very exciting. So I'm curious. Oh, no, go on. Sorry.
That's really impressive, both of you. We've done a fair bit of work with the robot hands, and there are lots of levels of complexity there, just getting the thing working, programming the different servos, working with sound, working with the vision. That's a really impressive project. Well done. Vijay, you had something to say?
Yeah, super cool. I was just trying to imagine, like, when it, like, as a prototype, totally makes sense how you have it set up now. But like in an ideal world, like if it was fully embedded, what would it look like in your head? If it was quote unquote a product.
If it was fully embedded, right? Actually, we're using Arduino Nano 33BLE Sense, and he got a lot of sensors, right? And we are using just the analog ports, right? And the digital output ports and the microphone. We probably could use something more specific for this case, right? We're using an ASCII 32 to some of our tests, and this example where we are using the gesture inference, we're using an ESP32 and a Node MCU 32S communicating with each other. So, and this is because of what Jeremy told right now about the challenges that we have with electromyography, right? So we have a lot of interference, electromagnetic specifically, and we had to get this out of the power sources of the electrical network at the region, and then using these development boards, we at the middle of the process, right, we were thinking about making something like more specific, but that would be necessary that we get out of the prototyping phase. So we have much work to do, and then we probably condense everything in a more non-degraded, right, PCB with less space, right? Optimized sensors and optimized circuits.
Yeah. One last question I have is like what would you say are like some of the difficulties that you have when you're trying to do this? Like what would you improve in the process of all the tooling or things like that would make things easier based on your experience?
Based on experience, it looked like a small tuning of everything that we are using, and with every detail, like for example, our cables that we're using to connect to the electrodes in our arms. If these cables got shorter, the signal, the relation about signal and noise got better. Right? So we are, and based with some of the previous work that we looked at, we have at the industry right now, like band, and a lot of new prosthetic devices that are being developed right now. We got some ideas to make this EMG like very close to the arm, and that's an example that we could get better with our jobs.
The sensor, no? I think the sensor is something that to be improved, no?
Right. The sensor is very sensible. It's very sensible.
Yeah, I remember I visited them at the laboratory, and they told me that they are doing a lot of experience with different type of sensors because this is an area that they should put attention, and I agree. You know,
we're trying alternative sensors too, and searching for right now. It's just a prototype inside the prototype phase. So we are looking for some research about PPG sensors and ultrasound sensors. As we got an example from Georgia Tech that with a professor called Jill Weinberg. Not good at names, sorry, but I think it's Jill Weinberg, his name. And they got a prosthetic arm, prosthetic hand with finger level differentiation with ultrasound sensors. And we're thinking about how we can use this to improve our project or PPG, or communicating with our PCB, and maybe using sensor fusion with EMG and maybe PPG, we don't know. It's a very embryonic phase, but we're searching for something that could get EMG better because he's very problematic. Right?
Oh, congratulations. Very good.
Yeah, that's a really impressive project. Thanks for presenting. Our next presenter, Marcello, you might be able to say this better. I just want to know if he's in the chat, but with a different name.
Ezzeldin, no, from Malaysia. It's
Uh,
good now. We went to Africa, to Brazil. Now we are going to another side of the world, to Malaysia. I think it's night there, no?
Yes, that's right. It's 9:30 here p.m. So yeah,
Thank you.
yeah. So I'll share my screen. 1 second. Okay. So hello everyone. My name is Ezzeldin, and I am a student in University of Technology, Malaysia. Well, technically, I finished my studies, but I haven't graduated yet. This is my actually my FYP project. It was under the supervision of Professor Muhammad Ridwan. I think he's with us here today. My project is about anomaly detection in the temperature of an AC motor using embedded machine learning, or TinyML. So, as we all know, machine learning solutions are being implemented in many industry areas. One of these areas is industrial maintenance. And so when machine learning is applied in industrial maintenance, it usually falls under the category of predictive maintenance. So in predictive maintenance, what we want to have is to get an estimate on the remaining useful life of a machine, or to foresee a malfunction before it occurs. However, can we implement this in all machines or not? Let's find out. So this is the contents of the presentation. So first, we're going to take a look at the problem statement, then the current approach limitations, and then the objectives of our project, and then the proposed solution. And we're going to take a look at some of the experimental results and the conclusion. So, like we said earlier, can we implement conventional machine learning approach in all machines or not? So, applying conventional machine learning approaches on some system can be expensive. So sometimes instead of applying a machine learning approach, maybe we could just replace the machine, and this could be less expensive than actually applying a conventional machine learning approach. However, this leads to another problem, which is that some machines would break down quite significantly due to the outdated maintenance plans. So the current approach and limitations, as you can see here, we have preventive or routine-based maintenance. And from the name, we can tell that a machine would run for a specific period of time. And after that time passes, we would run maintenance for that machine. However, this does not eliminate the risk of sudden breakdowns, and it's not very cost effective. So in the objectives of our project, we would like to develop a maintenance system based on a machine learning approach, of course, not from the scratch. But also we want to deploy a machine learning model on a low-cost device, namely a microcontroller. So for our proposed solution, we want to, with the help of the Edge Impulse platform, we want to train and test a machine learning model that can detect anomalies by monitoring the temperature of an AC grinder motor. Then after that, we want to deploy that motor on our microcontroller, which is Raspberry Pi Pico. And as you can see from the flowchart here, we want to calculate the temperature, and then the model will make predictions on whether there is an anomaly or not. If there is an anomaly, then the system will alert the user. If there isn't, we repeat the process. So let's take a look at the experimental results that we have. So first of all, we need to train our model. And in order to do that, we need to collect data. So this is our motor right here. And as you can see, the sensor is placed on the casing of the motor and then connected to an ADC. and which is connected to our microcontroller. We used the edge impulse data forwarder command line to directly connect our sensor to the platform. It's much easier and faster. So after collecting the data, this is an example of the data that we have. We have about 4 labels, and it's important to note that in our project, we use 2 learning blocks, a classifier block and the anomaly detection block. So we use the classifier. So we have 4 labels based on the state at which the motor is running at. So we have idle state when the motor is not running. We also have minimum, medium, and maximum label. It's based on the temperature of the motor. So what we see here is the training, the model training results for our classifier. As you can see, we have an accuracy of 95%. And then after training the model, we use the test data that we have to test the model. And this is the test result that we have. It's 90%. We used, like I said, an anomaly detection learning block in the Edge Impulse platform, and it uses k-means clustering. We're going to discuss that later. So after testing the model, we can now download the model, and then we have to modify it a bit so that the model could be connected directly to to the sensor to receive data directly from the sensor. So this is after deploying the model on our microcontroller. I'm not sure if you can see here the anomaly score. It's 0.008 in one entry, and on the second entry, it's negative 0.008. The reason for the negative here is, like we said, the block uses, the anomaly detection block uses k-means clustering. And what it does is that for a new data point that the system receives, how the data is grouped in, our data is grouped in clusters, in a number of clusters. And when a new data point is received, the anomaly score is calculated by finding the distance between the new data point and the edge of the closest cluster to that new data point. So if we get a value in negative, it means that the point is inside one of the clusters. So this is the final circuit. As you can see here, we have an LCD display to show the temperature of the motor in real time. We also have some LED lights to indicate the state at which the motor is running at. And we also have a buzzer to alert users when anomaly is detected. So right now I'm going to show you some videos for each state. I'm going to show you the output of the serial monitor and the output of the circuit itself, this circuit. So this is the output when the motor is running at minimum condition. The video is also fast. The playback speed is faster than it normally is. So as we can see, the LED lights will light up when the motor is running at minimum condition, and these are the predictions right here in the right hand side. We can see it's 0.74, I think. So this is at minimum condition. So as we can see, the orange LED will light up when the motor is running at medium condition. We can see the predictions here. Sometimes the motor will confuse between medium and minimum condition, so it's given it a 50-50 chance. This is at maximum condition. The red LED will constantly light up. And then finally, when anomaly is detected, the buzzer will actually make noises, and our red LED will blink at this point. So in conclusion, we can actually run the model independently. We don't have to connect it to a computer or anything. So also we can add other features to our model, so we can make it a bit more user-friendly. So we can, for example, develop a control circuit. So when anomaly is detected, the the system will automatically shut down, and then wait until the temperature normalizes to run back again. And yeah, that's what I did so far. I'd like to thank Professor Mahmoud for the advice throughout my semester, and that's all for me. Thank you so much.
Oh, great projects. I like it very much. Only a question. I mean, of course you monitor temperature, and temperature is, but of course it's related with the working. You know, the how much current you are taking from the motor, or the motor is using. You know, is like a load. No, it's related with the load that you do. I think it's related. And what kind of anomaly you did? What means anomaly for you? As in vibration or whatever?
The anomaly is when, I mentioned we have 4 labels. So we have idle, motor is not running, and minimum, medium, and maximum. So anything outside of that is considered as anomaly. So when the temperature is increasing more than it should. In the beginning, we thought about the change in temperature. We wanted to add that. So if the temperature changes in a way that is, so it's rapidly changing, maybe we could detect that too, but we couldn't add that also. So we're monitoring like the average temperature. So in a specific, so the model will take about a data of 15 seconds worth of data, and then calculate the average and get the maximum temperature. And based on that, we can, the model will make a judgment on whether there's an anomaly or not.
For example, could be that the load is over the maximum permitted, something like. So you try to prevent it's broken, you know, something like. Okay. Oh, very good. Guys, by the way, only we have more time to questions. And because we have 1 hour and we are very short in time, okay, the 4th presentation from University Javariana from Colombia will be postponed for next section. So I thank you, the guys from Diego and from Abelardo. So we move for next session. So have a little bit more time for question now. It's okay. So fantastic. No, very good, very good. It's only return to the motor. I mean, it's interesting to see some kind of temperature is one thing, but to do some sensor fusion, you know, like including signs or vibration, or so how all this together you can prevent what's going on with the motor, no?
Yes, that's right. That's something I was thinking about also, like add other parameters to monitor other than just temperature, maybe the vibrations of the motor and whatnot. Yeah, that's right.